Hello once again, and we have wrapped up with the double and half angle formulas. So I have another set of identities to introduce right quick. They're not of major consequence, but it's rather clever how they were derived. So I'll go ahead and get into those. And then we will round out the video with a few more examples of doing proofs with identities, using identities. So here we are once again with our half angle formulas. We had worked around with the double angle formula for cosine to get these. And let me go ahead and tell you, if I haven't said it a million times already, it's a very mathematical thing. It's a very profoundly mathematical thing to say, okay, I've gone through all this trouble. I've found this formula. I found this identity. How else can I use it? What else do I get for free with it? How else can I write it so that I can make it as versatile as possible? And what we can do with these formulas right here, for instance, with sine or cosine of x over 2, we could, recognizing this is an equation, square both sides and get sine squared of x over 2 is equal to just now this expression, 1 minus cosine x over 2. And then we can solve for the cosine in terms of the higher order, or kind of just leave it as is even. And actually, if we had sine squared of x over 2 equaling 1 minus cosine of x over 2, with just a little bit of relabeling, we can turn that into what we'll call a power reduction formula. Right? These formulas right here are all consequence of squaring both sides of the half angle formulas. Well, this one right here for tangent, of course, is just a consequence of sine over cosine. But this is yet another way of using the half angle formulas. So if you ever had an expression such as 1 minus cosine x all over 2, you could just call that sine squared x. And there's a more roundabout way of manipulating that formula to get to sine squared x, but we can do it directly now using the power reduction formula. So it's just an even different way, yet another different way of writing the same result. And we do that because we have less manipulation to do in order to use each of the identities. And that's going to be helpful. That said, at the same time, the power reduction formulas, by virtue of not being anything new, doesn't bring anything new to the table, but it's a matter of convenience. It's a matter of quality of life. And it is a nice boon to have something like, oh, I've got this thing right here, 1 minus cosine 2x over 1 plus cosine 2x. I could do the double angle for cosine, do the double angle for cosine again, and clean that mess up, and hopefully eventually, assuming I did it right, I would end up right there at tangent squared 2x. Or, recognizing that I have this identity now, I don't have to do any of that. Having this form, having this expression, automatically is tangent squared of x. And that is the power of the power reduction formulas. But I digress. Let's do a couple examples here. Not necessarily using the power reduction formulas, although possibly being able to. Let's see what else we can do. Suppose I wanted to prove the identity that tangent of x is equal to sine 2x over 1 plus cosine 2x. Suppose that's what I wanted. Well, there's actually a couple ways of going about it. I've got one right here. One option is, of course, to use the double angle formulas. I've got sine 2x, that's 2 sine cosine. I've got cosine 2x, that's one of three things. But if I choose the form 2 cosine squared minus 1, I get to knock off the 1 with this one. And so the remaining expression does clean up very quickly to be just tangent of x. Now, if I had picked one of the other forms for cosine 2x, I would still eventually get the tangent of x. I would just have to do a substitution using the Pythagorean identity along the way. Could be done, though. Now, here's the question, and here's the question that I get asked a lot, is what's the right way to do it? What's the answer? Well, here's the thing. Here's the answer right here. It's given in the problem statement. The answer is yes. The answer is yes, this is an identity. So it's not the answer that's unknown. The answer is known. The answer is yes. The problem is, how do I get to that answer? Not what is the answer, but how do I get there? And there are more than one ways to get to that same answer. In fact, this is almost like tangent squared x. So maybe with a bit of clever substitution, I could turn sine 2x over 1 plus cosine 2x into 1 minus cosine 2x over 1 plus 2 cosine 2x, maybe inside a square root, ultimately ending up with tangent of x. Just kind of throwing that on the wall there. Could happen. Could happen. So that might be a third option. Another option, I guess this would be actually the third, would be, well, recognizing that, yeah, 2x is double x, we could also say that x is half of 2x. We could try using a half angle formula on tangent here. In fact, if we did that, right, recognizing that tangent of x over 2 or u over 2 is one of these two forms, wait, sine of u, 1 plus cosine of u, sine of u, 1 plus cosine of u, in just a single substitution, we can turn tangent of x into tangent of 2x over 2, which is now, for the half angle formula for x over 2, now for the half angle formula for 2x over 2, becomes sine of u, 1 plus cosine of u. There's 3 ways that we've got just right there, probably more, probably several more. It doesn't guarantee that everything you try is going to work, but it does promise that there's more than one way to get where we need to go. So with that in mind, I've got a question for you, and we'll pick that up here in a second. I want to verify the equation that 2 cotangent of x is equal to cotangent of x over 2 minus tangent of x over 2 is an identity. So again, the issue is not what's the answer, because the answer is yes. The answer is yes, it is an identity. The question is, how do I prove it? How do I verify this is always true? And there are possibly many ways of getting there. Here's some that I've listed right here for us. One strategy might be to start with the right-hand side and just use the half angle formula for tangent twice, right? Here's tangent of x over 2. Cotangent is 1 over tangent of x over 2. So use that half angle formula twice and work with what you get, and hopefully you'll get to cotangent of x. Maybe that's a valid strategy. Or again, like we had suggested on this previous slide, rewrite x here on the left to be 2x over 2. And do the double angle formula for tangent, because this is 1 over tangent x, except now the angle in question that we're doubling is x over 2. Another option might be to start with the right-hand side, and so this over here, write everything as sines and cosines in x over 2, combine your fractions and reduce accordingly. Maybe that will get you to 2 cotangent x. So you tell me, what is an appropriate strategy here? Is it one of these? Is it more than one? Think it out, take your pick, and we will see what we can do with these ideas. And yes, it's all of them. All of these strategies, and probably more, all of these strategies here are valid, workable strategies to verify this equation as an identity. Let me show you what I mean. Strategy 1, start with the right-hand side and use the half angle formula twice. So we start with the right-hand side, write it so that we can use the half angle formula for tangent twice, so that's 1 over tangent. And remembering also that with half angle formula for tangent, we actually have 2 choices. We can have either, let me flip back up here for the half angle, either sine x over 1 plus cosine x or 1 minus cosine x over sine x. And again, the plus or minus depends on whatever we're in, but I think that's going to work out so we can safely drop that for this proof. But anyway, we can either use this form right here or this form right here. And actually what I think we want to do is both. Because I want at the end of the day 2 cotangent of x. That's cosine over sine. So I need to make substitutions that give me fractions over sine. So if I choose for the first sine x over 1 plus cosine x, after substituting and recognizing I'm in a reciprocal, I've got 1 plus cosine x over sine. Doing the other form for the other term gives me 1 minus cosine x over sine. All of this is now over sine. Again, right, if I had picked other forms or done it a different way, I would just have to done some manipulation to get the same denominator. But in having picked these forms the way I've done it, we can now directly add them together, or subtract them, right? We can directly combine our 2 fractions. So 1 plus cosine minus 1 minus cosine, that becomes 2 cosine x over sine x, 2 cotangent x. So yes, strategy 1 is totally legitimate. Strategy 2, start with the left-hand side, so start with 2 cotangent of x, and use the double angle formula for tangent. Now let's give it a whirl. 2 cotangent of x is 2 cotangent of 2 times, or double, x over 2. So using our appropriate formula there, which is actually a double angle formula for x over 2, we get 2 times, right, the 2 still there, 1 over 2 tangent of x, 2 tangent of u over 1 minus tangent squared u, or where u is x over 2, 2 tangent of x over 2 minus 1 minus tangent squared of x over 2. The 2's cancel, right, the 2 out front and the 2 from our substitution for the double angle formula for tangent. So I've got 1 minus tangent squared all over tangent, where the argument of our tangents are the same. They are x over 2's. So I can do a little term-by-term division here. I can split up this fraction. We got 1 over tangent of x over 2 minus tangent squared over tangent. And so that cleans up to have the right-hand side. So, yes, another one. Another valid strategy found. And the third one also works. Right, if all else fails, if you have no idea what to do, you can always just write things as sines and cosines and go from there. So we can write cotangent as cosine of x over 2 or sine over x over 2. And tangent is sine over x over 2 over cosine of x over 2. And yes, we could do the half angle formulas 4 times over here. But before we mess with that, let's combine our fractions. Let's get a common denominator, add that all together. And that gives me cosine squared of something minus sine squared of that same thing, which incidentally is a double angle form for cosine of 2x, or 2u. And here I've got cosine of u over 2, sine over u over 2. That's 1/2 of a double angle for sine. So making the appropriate substitutions this way, we've got cosine over sine all over 1/2, or 2 cosine over sine, 2 cotangent x. These 3 and possibly more ways work. So yes, there's more than one way to get where we need to go. It's our job not to identify what the answer is, because we're given the answer. Our job is now to identify and map out and chart out and actually drive to the solution using unknown methods. And it's not just one single right way. There's not some weird contrivance where you have to hop on one foot and spin backwards or anything like that. There's more than one way to get there. You have to decide a way and work it through. And just because the way you tried didn't work doesn't mean that there is no way to do it. You just have to look creatively, cleverly, and see if there's another approach that you have not tried. Because in this class, I will not lie to you. If I say that something's an identity, I mean it, and there is a way, and arguably more than one way, to show that. So that's going to be our job for a while here. Once we're comfortable doing that, we will then broaden our horizons into equations that are not always true, and then we'll worry about what makes them true, what makes them false. But for now, the job is simply, can we show something we know to always be true to actually be always true? And that's it for now. I will let you know what's coming down the pipe. We will have just one more set of formulas here, one more set of identities in this section of proving identities and using formulas. And so after that, we will get into trigonometric equations. That's rather exciting. It's rather exciting to marry the trigonometry with the proofs, with the algebra, actually, that we'll get to in the next set. So I'll see you then. Let me know what you're worried about. Let me know what we've just covered is the most confusing to you, and we'll get that addressed as soon as we can. Have a good one.